Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Tony Hay and the Technical Computing Group. We decided some time ago that it would be a good idea to have someone run through the history of parallel computing, given the importance of parallel computing these days due to the emergence of many core architectures. And we thought of Jeffrey Fox as someone who has experienced everything in the last 20-30 years in parallel computing as the best person to do that for us. Jeffrey is at the university at Indiana University of Indiana, or Indiana University, I'm sorry. He's a professor there, and he's going to take us through the next few days through the fascinating world of parallel computing, and I'm really looking forward to that. So, Jeffrey, all to you now. Thank you.
Thank you. So I hope you ask some questions, because it is rather difficult to know exactly what to speak about. So please ask questions. So I'm not really going to describe this historically. I would just describe what I think is known about parallel computing over the last 30 years. There is some history here, because many of my slides are actually 10 to 15 years old, because some things haven't changed. So as I understood, the purpose of these lectures are to remember what happened in parallel computing, so that we can use them in multi-core or many-core systems. And my expertise is not hardware, so I will not discuss hardware very much. I'm not certain my expertise is software. I would say my greatest expertise is applications. So I will describe everything usually from an application point of view, which has possibly been the most successful in parallel computing. And I will assume the task is to understand how to use 32 to 1024, that type of range of parallelism, cores. That's not what you have today. I don't believe you need to do sophisticated parallel computing to use today's many multi-core or multi-core chips. But soon you will at least be in the... Oh, it's not on? I thought he switched it on. I didn't. It's now working? Yeah. I don't think I did anything. All right. So I will assume that we're trying to produce parallelism of 32 or more, because that is likely to be what you need in the future. And we will discuss what good is and what scalable is as we go along. So there aren't too many recent books on parallel computing other than relatively straightforward ones describing how to program in MPI and things. The last one I wrote was with several distinguished authors, including Ken Kennedy, who just passed away. And that is a reasonably good book, in my opinion, the source book of parallel computing. It has a chapter or so on everything. I should note that I will only make very simple remarks usually. And the reason to make simple remarks is that in something as complicated as parallel computing, unless you have a principle that's simple, it's not likely to generalize. So I will try to state things in a simplistic fashion because they might generalize. It is, however, true that the reason why parallel computing has been very tiresome is that the implementation of these simple ideas has proven to be incredibly difficult, especially for complicated problems, even though those complicated problems have the same features as simple problems. So you can see that in parallelizing compilers, that people have tried for a long time to implement things you can state in a few lines, and it is proven to be extremely hard. As Saras knows, I produced a set of references which are useful for this course, and if you like to use Conatea, which is nature's referencing system, you go to conatea.org and you look for the username CRMC, and you will find a set of some 150 online references labeled by various tags such as MPI or applications or Multicore or things like that. All right, so it is important to decide on what problems we're talking about. So when we started off doing parallel computing, we only focused on what I would now call closely coupled problems, which in this little picture at the top are those A1, A2, A3, A4, which, at least if you're running on a that could be solving a partial differential equation, or on a client computer it might be various image processing in Photoshop or something like that. And then you have, at least here, we have two other classes of problems. One used to be called embarrassingly parallel and is now called pleasingly parallel. Those are just independent jobs. They have become far more popular than they used to be because the grid is dominantly connected with pleasingly parallel problems. And so as they're very successful on the grid, they've grown in importance, at least in terms of the literature. I don't know if it... there's also a class of loosely coupled problems, which, if you like, is workflow on the grid. And you could say what browsers do has a lot of loosely coupled components, because they have, and if you like, you can try to quantify this. Tightly coupled has latencies of microseconds. Loosely coupled is between milliseconds and seconds, or several seconds. And the task of implementing those is quite different, and the application characteristics are different between those types. Now, I would say the parallel computing is focused on tightly coupled problems. The reason being is that if you look at the loosely coupled problems, they tend not to have a lot of parallelism. There's just not a lot of things to couple together. And for embarrassingly parallel,
Question.
Yes.
Do you distinguish between strongly coupled, tightly coupled, and closely coupled?
No, I don't. No.
If they're synonymous.
To me, in this talk, they're synonymous. If somebody's defined the difference, wonderful.
I just want to know.
No, I do not distinguish. I mean, operationally, it is a microsecond versus a millisecond, or seconds, is, I would say, the critical difference. And so I, again, would say that if you only want to do embarrassingly parallel or loosely coupled problems, then there are no serious challenges. I believe it is understood how to do those problems. I'm not saying they're trivial at all. As we know from the huge amount of work on the grids, they're highly non-trivial. But I would say that there aren't difficulties in principle. Whereas for tightly coupled problems, I would say there's serious difficulties in principle in doing those. And I would assume, maybe incorrectly, that we have to do tightly coupled problems if we want to make good use of many core chips, because there's not enough parallelism of the other sort. That might be wrong, but that is that underlies at least my research and how I think about this problem. That one of the challenges in multi-core chips is to find how to identify tightly coupled parallelism on clients and then implement it. which is not to say the other is unimportant, but I don't think it will scale to huge numbers of cores in a straightforward fashion. Of course, there are problems which are like embarrassingly parallel, which have huge parallelism. I mean, the physics, the data analysis of the Large Hadron Collider will have whatever it is, 1 billion events, each event which can be processed independently. But those are all those are essentially server problems, not client problems. So servers have lots of examples of pleasingly parallel jobs, whether it's processing users on a web server farm or analysis of experimental data. Those are all pleasingly parallel server applications, which I think will be straightforward to implement. But so I will not discuss those significantly in these talks. So that's sort of what so this states again what I said then. I sometimes call the loosely coupled meta problems because and you can think of a world where you sort of have atomic problems, sort of nuggets, and then you join them together, you compose them, you orchestrate them, and you get these meta problems. And operationally, operationally, there's an important difference between meta problems and parallel computing. In the meta problems, the problem is composition. You're taking a job that's already decomposed and joining it together. In parallel computing, you're taking a single job, process an image, solve a differential equation, and breaking it up. And so superficially they look similar. They're both actually entities running in parallel. One is composition, or orchestration, or whatever you want to like to call workflow, and the other is decomposition. And decomposition is the one that's hard because decomposition is ambiguous and it requires digging into the internals to decompose a problem elegantly stated in a non-decomposed fashion. So parallel computing is hard. If you like, grids in inverted commas are easy, in my opinion, comparatively, because they're composition and largely independent activities. So they're enormously important and difficult to implement. Parallel computing is quite hard because it involves decomposing problems which are decomposable but aren't decomposed. That's why there are all sorts of possibly deep issues as to whether objects are useful here, because you're dealing with a problem that's not naturally broken up, whereas the totally independent or loosely coupled, they're already broken up, essentially. So most tightly coupled problems are usually can be termed as being data parallel. And data parallel is probably used in slightly different ways by different people. And I will give you lots of examples. But for me, data parallel means that we have a problem with a set of entities in it. Grid points, pixels, people, internet nodes, and we have an algorithm to evolve those entities either as an iterative algorithm or as a time-stepped algorithm. And the data and this set of entities has natural parallelism because these things evolve together. And that's a data parallel algorithm. It comes because the problem has lots of parts. So, although you do not usually express the problem as a set by breaking it up into the parts, you usually use arrays and loops and things to describe these parts. But at its heart, the problem is a set of entities with an algorithm applied to each entity. It does not have to be the same algorithm. Often it is. It's usually a related algorithm, otherwise it wouldn't be the same problem. And the features of data parallelism is that the parallelism is enormous. It is not. It is, people seem to think it's surprising that you can get, say, speed-ups on 250,000 node machines. I think it's rather obvious you can get speed-ups on those machines because the parallelism from data parallelism is measured in billions, not in tens as you do from functional parallelism. And these data, so data parallelism is usually scalable. You usually can extend it. It's subject to performance issues. It is pretty hard to express when the connection between these entities is a little obscure. And it, all the standard parallel approaches tackle data parallel algorithms, whether that be message passing, the various parallelizing compiler approaches like high-performance Fortran or OpenMP. Those all they all tackle effectively data parallelism. They tackle other things as well, but they certainly tackle data parallelism.
So if you have the problem that it's a sequential in nature for the data, so does parallel program, parallel, the kind of things you
Yeah, so that's, I come to that. I come to that when I attack Amdahl's law. So, yes.
For the benefit of those who are watching us, can you please repeat the question?
Okay, so the question was, can you use parallel computing on a sequential algorithm?
approximation?
And the answer is essentially no, although people can presumably find an algorithm which is not sequential.
But it's an approximation.
Well, you see, there's another important point, which is why ultimately I believe Amdahl's law is misleading. If you have a sequential problem, it is very unusual it will take any time to execute. It's usually very quick. It's gone. The only reason that these problems take a long time to execute is there is some additional degree of freedom other than time that makes it execute for a lot. Numbers of pixels in image processing, number of mesh points in a solution of an equation. That's what makes it take a long time. The one example I found of a science problem that took a long time was if you wish to study the solar system, whatever it is, 14 planets or I don't know what they are. That is an essentially sequential problem. And if you wish to evolve that for a huge length of time, that would be very hard to parallelize, except for the parallelism over planets. You can do it, the parallelism over planets, but that's it. You can't do any parallelism over time. But there are essentially no important scientific problems of that type.
So, for example, I work on speech problem, which is sequential in time.
Yes.
And many people are talking about how to approximate that sequential decoding problem in such a way that parallel, computing can help. I just wonder whether this is a valid problem to solve.
Well, obviously, if you take a problem like that, which can be divided up into segments, you can apply separate programs to each segment and join the segments together. So that one is, if you like, data parallel because each of the signals is a separate data point, and so you can use.
They are parallel, but still within a segment is parallel.
That's right. Well, you do it sequential within a segment, and then you do multiple segments in parallel. But that's how you do all of these problems. Every single data parallel problem, well, I've drawn this thing here, which is whatever it is. It's an 8x8 array. So this might have been, let's say a 256 by 256 set of mesh points, and then I decompose it onto an 8x8 set of processors. Each processor would then have whatever it is, 32 by 32 data points in it. So you're always, and I'm going to make this point, you always have a mix of the data parallelism and the original sequential implementation. And that's true of all these problems.
But to me, the difference between this and the sequential problem is that the computation for a particular point depends upon other points.
Yeah, this is certainly different from your speed.
Process, it doesn't require that, right? Because it can process individual blocks separately from each
Yes, so
other.
image processing is like solving differential equations. It can be done, it has natural data parallelism because you can think of it as updates. The speech processing is a little different. You have to make some approximations and some sort of different algorithm to make that work.
Okay, so, but is that part of the parallel computing category that people talk about is something that I haven't studied.
I'm not aware of a lot of work on speech processing.
Can we continue?
Oh, yeah.
Yes.
Question?
Yes.
If you think about the client instructions executed last year, let's say 10 to the 25 instructions executed last year, how many of them were data parallel?
I would assume rather few.
I would too.
Yes.
So I'm trying to get a sense of, you talked about multi-core going into clients. Is this a big problem or a small part of the problem?
Well, I would assume that is Intel and Microsoft's 64 billion question, isn't that right? What type of problems will you be running on multi-core that would use 72 nodes or whatever Intel will deliver 5 years from now? I think you're going to find it relatively hard to take the current type of job mix and make it use 72 cores very efficiently. So I suggest that you're likely to need other types of applications, such as speech processing and image processing and things like that, which have more natural parallelism.
Do you have the current job mix in the presentation somewhere?
No, I don't know. I wasn't trying to sell you on that point.
No, you're the expert.
I'm the expert on the last 25 years of parallel computing, and parallel computing has essentially only been applied to scientific applications. Only. Because they're the only ways we found any parallelism. We failed to do any parallelism essentially outside scientific computing and databases and things like that. Yes.
There are two areas where parallelism is currently actively used, and that's scientific computing and databases, and that's about it.
No, we do. Search uses massively parallel computing.
Okay, that's
And
in addition to these pleasingly parallel applications.
Yes, so I would say there's, if you like, the grid is a huge, or the internet is a hugely parallel system, but it's doing the incredibly loosely coupled / pleasingly parallel application. And you can do those, of course, on multicore, if that's a good use of multicore. And it is presumably a good use. So you can extrapolate the grid to server multicore straightforwardly, I think. So I think you can be reasonably sanguine about the server side. I don't think you can be so obviously sanguine about the client side. So this is just a simple slide on the so-called functional parallelism, which has been around since the beginning of parallel computing. And all applications have some sort of functional parallelism, but as far as I know, nobody has ever got more than a factor of a few from them. And they've done heroic tasks like run an ocean simulation here, and a climate simulation here, and a glacier simulation there, and I don't think anybody cares, because the gain you get from that is so modest as to be irrelevant. But you can do functional parallelism of at least in science, the functional parallelism is modest in size because there are only a few tasks. And so here's some examples of these meta problems. And I would assume we should just copy grid workflow or mashups to do this type of problem. And it is better to follow. I would not follow the parallel computing approach for this type of problem because I don't think it's as advanced as what people do today for workflow or mashups. I will make that point later. I mean, again, a long time ago I was told I used 10,000 programs to build an aircraft. That's what people from General Electric told me. And these are all other examples of this type of problem. Something we might want to discuss at some stage are event-driven simulations, because they're a problem class which has been in my opinion, highly unsuccessful on most parallel computers, but could run a lot better on multicore, because discrete event simulation, because it has, at least in the simplest implementation, a centralized queue of events, ought to run a lot better on a multi-core chip. And looking more carefully at that particular model of execution, it would be something which is worth thinking about, in my opinion. So we'll come back to that. But DoD has wasted billions of dollars on discrete event simulation, and basically, as far as I know, written it all off as a failure because it did not work. But there were other reasons other than that wasn't, I believe, due to the methodology. It was due to the fact that it took too long, so the software was out of date when they built it. Right, so this again, states the task again, that we're going to try to understand the issues in using several cores, and we will do that by just explaining what people learned and didn't learn from the last 25 years. So we discussed what's going to go on a core. So Intel has some statements about what will happen on a client-side machine. And I just stole 3 slides from Intel. And the only purpose of these slides is that, as far as I can see, the applications they suggest are actually data parallel. They're not the traditional client-side applications. They're rather large-scale data analysis and data search applications which would be natural for multi-core chips. So probably Intel realized that when they made the suggestion. But if Intel's suggestions are correct, that you're going to have things like this. Here's some sort of medical application, and because that could probably better run on a server, but they put it on a client here. And there's their stack. This stack is, I would view, a data parallel stack. These are largely classic scientific, or I would say machine learning is typically, I would say, a scientific algorithm. These are iterative algorithms often, and so they are amenable to standard parallel computing techniques. So this class of application, in my opinion, will straightforwardly run. They will run with hard work on multi-core chips, and I do not expect fundamental problems in principle in making it work. Yes?
Does the multi-core architecture have a shared L2?
But it could. I mean, it depends on the vendor. I don't think those issues matter for the success of these things. Because if you look at what's holding people up, they're much cruder. The problems are much cruder than whether things the caches are shared or coherent or not. They're trivial problems that you can't actually identify the parallelism and things like that, which are this fundamental difficulty. Not.
That may be true, but that's the reason Intel lost out the first generation.
That's right. Yes.
That is the core reason.
Well, see, I may be wrong, and we can discuss this, and maybe I may well be wrong. My impression is that compiler-generated parallelism has not been very successful. And it's not obvious that it will be any more successful in the future than in the past. And I think it's not, and unless people are very optimistic, but they made the same statements let me think, when did they do it? 1987. So that's 20 years ago. They were equally optimistic 20 years ago, and they are still unable to do quite simple problems, certainly not the hard problems you want to do. And I think it's not that they're incompetent, it is, well, it's a point I'm going to make. When you write software, you throw away a lot of information. And that information, unfortunately, is needed to determine the parallelism. So that's why I say there's a harder problem. The problem is not that the compiler is needs some sort of help. The problem is the compiler cannot find out what is necessary to parallelize the application.
Doesn't this lead to a deeper question, meaning maybe we have the wrong way to express our problems? I'm coming from the database area.
Yes, I think it does.
If you use SQL declaratively, you have a chance in a very small and tiny area to make progress. So don't we have to look for different paradigms?
Definitely, and obviously Microsoft Research is trying to do that. You have a lot of effort in languages. The only thing I notice is the same statement was also made 25 years ago, and we still have not found a new language which has made any impact whatsoever. If you look at scientific applications running today, I think the only change is that some of the Fortran has migrated to C++. That's it. They're still using message passing. MPI is the only significantly used technology which is message passing in the large scale applications. And there is some modest migration of Fortran to C++.
What do you think of MapReduce as a new language?
I'm afraid I don't know that.
So I mean, to me, given that SQL has been successful at being that, it sort of raises another interesting question, which is, do you think that Turing complete languages are fundamentally intractable?
Well, I'm afraid, again, I don't quite understand that. Well, the question was, are Turing complete languages intractable? So I will have a few slides which you can ask me that question again at, because you might be able to answer it in a way I understand. I should note that I have a PhD in physics, not in computer science. So I think about things from a slightly different point of view. All right, so this slide I would say is optimistic in the sense that if this is a reasonable vision as to what might be present 10 years from now on a client, we could certainly have a program to implement all of this. We might still need another program how best to implement it, which we can use this as a discussion to motivate. But this will succeed. If they put down here Microsoft Word, Microsoft Word, Microsoft Word, I'm not certain we could succeed, because I wouldn't know how to do that.
So the point is that those algorithms that you put there are supposed to be easily written in maybe even higher language than the one we're used to now.
At least, well, I would say from the application point of view, I can look at these applications and parallelize them.
Automatically, not.
No, I didn't say automatically. No, I would not say automatically. No, I would no. I would just say, I mean.
No, but it's good. Now we can do that, right? I mean, if I look at a particular algorithm, just look at the name, I know this will be parallelized. So.
And you see, it's not so obvious. We can again.
Except particle filtering. Otherwise, everything else seems to be parallelizable.
Yes, and we can also, of course, build libraries. And so it is not so clear that we can just reserve parallel computing for the Marine Corps. We'll build the libraries, and that's it. And then we'll use workflow and stuff, which the masses can use, and build the client applications of the future. It's not so obvious that you need parallel computing for the masses. You may do. It would be wonderful if you did. But if certainly Department of Energy has used the Marine Corps to do parallel computing, and this ASCII and things like that have spent, and SIDAC have spent huge amounts of money, but they've been pretty successful. They have taken extremely complex codes and parallelized them with very, very good results. And extremely good libraries. Jack Dungara and others have built extremely good, highly efficient, very reusable libraries. The use of libraries is a highly successful technique. And all of this stuff here can be done as libraries, I think. All right. So we've said some of these things already. So as far as I know, most large applications can be parallelized. The problem is that parallel computers don't look like applications. They look like parallel computers. Another good statement, which may or may not be true, is that any significant piece of software cannot be parallelized. That is basically what Amdahl's law said. That if you look at a piece of software, you stand no chance in general of parallelizing it. Even the case where parallelizing compilers have been successful is because the user was very careful how they wrote the software. If you took a general piece of software, including scientific software, and handed it to any compiler, there would be no chance of parallelizing it. So that's why different expressions and functional expressions and all, I mean, declarative ways, all those are quite interesting because the current mode of expressing applications in software throws away information. And it states here that parallel computing works because Mother Nature is parallel. We're simulating Mother Nature. And it's sort of interesting. When people build things, if they build software, they make it non-parallelizable. When they build other things, they make it parallelizable. Like Microsoft is parallelizable. We can think of Microsoft as a bunch of buildings, and each building is a bunch of rooms, and there's modest communication between them. And so we could imagine simulating Microsoft. Well, we probably couldn't imagine simulating them parallel, whereas we find it hard to simulate a piece of, Windows. We couldn't run Windows in parallel very well. All right, so here's a language I like to use to explain this, which is something to do with the theory of complex systems. So you can think of everything we're talking about, whether it be software or applications or computers, as a bunch of entities arranged in a space, and there's some sequencing, which is often time, can be iteration count, clock sequencing, what have you. And the task of actually writing software or using a computer is mapping a problem onto the computer. And at least in science, that would come from, you start off with Mother Nature. Some brilliant person builds you a theory. You make a model for that theory. You convert it into numerical form. You write it in software. You hand it to a runtime that puts it on a computer. Each of those things there has some sort of space and some sort of time usually associated with it. And when you do this act, you're actually mapping one into the other. And the problem is, when you do these maps, you obviously throw away information. They're not invertible. And by the time you get to the software, it has thrown away typically the information needed for the parallelism. Or if it's still there, that information is buried in the runtime. And so only the runtime will tell you whether a certain dependency is or is not there, allowing you to parallelize it. So you can think of sort of one Neumann model of computing actually as taking the space and time of problems and mapping it into time, just a sequence, single sequence. So that's the von Neumann model. And the problem with that von Neumann model is when you map it into a single time sequence, and now you want to run it in parallel, you have to unmap it. And when you've mapped it into a time sequence, you do not know which parts of those mappings were gratuitous, maybe just because you had to do something first, and which were intrinsic. Because for parallelism, you need to know the intrinsic sequencing of your operations. And so this comes back to the point about better languages and new ways of expressing it. It is clear that the problem is built into the way we express things. The only other problem, it's not quite obvious that Mother Nature uses a declarative language in specifying its operations. So it's not quite clear to me when I look at the grass growing that they're actually following a declarative process. I think they might. They're not so obvious to me. All right, so that's that. So we're trying to build maps. And we're trying to, the most fundamental, we must preserve correctness, and then we need to then get as much efficiency as possible. And of course, what we think is getting efficiency on sequential computers ends up as seemingly destroying the parallelism information, because we introduced too many additional things that seemingly needed to get efficiency on the sequential machine, which ends up confusing the possible parallelism. So there are various ways you can try to address this, of which probably at least the one that's been looked at most is just to use higher level concepts such as arrays or index sets and things like that. And obviously that has to be a reasonable idea, and in some cases it works very well. It, however, has never been implemented, as far as I know, in a successful general fashion. I mean, there's this famous example of high-performance Fortran, which was basically a failure, which did relatively larger number of array operations. The so-called HPCS languages, which is DARPA's High Productivity Computing Systems project, they all have some sort of array parallelism in there. But as far as I know, and it appears much more general than HPF, and so it stands a chance of success. My only concern is if I look at OpenMP and the work done in that area on parallelizing compilers, it doesn't seem to have parallelized anything very significant. And so it's a little worrisome that the compiler technology needed to take arrays and make efficient code is very, very difficult.
But you see, I think already the structure array is wrong because it's a sequence, and the sequence is inherently sequential.
Yes.
I think that's what we learned in databases, because we talk about sets, and you take the sequential aspect away, and therefore you get a much broader space of making decisions. And I think that's, from my point at least, the reasons why those things cannot be successful, because, again, arrays have already the sequential part built into it. And taking it out again is more than difficult.
Yes, so I'm not quite certain in the database analogy where the dependencies come in, because the critical problem, of course, in these data parallel algorithms is that certain points are linked to certain other points, and how you express that, and what's most important for the compiler, how you implement that efficiently, that's where the compilers usually fall apart. They've learned how to implement some of these things in a reasonably well, but they certainly haven't done very many very well. And the only thing that worries me is this is now, what I said, 20 years. And we better have a revolution if this is going to be useful 5 to 10 years from now. There has to be a quantum change in the quality of this technology. It may just need more people. I mean, if Microsoft just poured all its resources, maybe that's what it needs. Currently, the combination of the rather small amount of federal funding, because federal funding has largely dried up in this area, and the DARPA funding does not appear to be advancing things very fast.
So I think the real problem is that we haven't felt that we've had to solve this problem. And the real reason is because the clock speeds have just kept going.
That's right.
Right? And these problems can be solved. I mean, as you pointed out, there are applications that could benefit from solutions in this area. But we haven't needed to do that because it's just been easier just to buy faster clocks. Now, if that isn't an option, then I think you'll find people thinking, really banging their heads much harder on these challenges.
Yes, so I consider it very useful to bang people's heads harder on this, because the current rate of progress is not very impressive. The HPCS languages, I think, have many more years before they're meant to be testable, and they're all unproven concepts.
The real demand for those solutions hasn't really materialized because, it's all predicated on there not being a simpler solution, which is just to buy a faster clock.
Yes, so that's presumably the motive. That's presumably why they dug me up from the past and placed me here. You see, Rip Van Winkle went to sleep 20 years ago because he couldn't solve the problem, and there wasn't enough resources. So now maybe the problem is more important, and so maybe more resources will be put onto it.
Yeah, actually, I'm pretty struck by the earlier comments that the nature, the mother of nature actually is parallel.
Yeah, Mother Nature's parallel.
True. But every time we engineers or computer scientists think about the problem, I think we are typically, some of my work is in the model stage and numerical stage. And the way we think about this modeling, during that process, we think about how, software can be implemented. In that case, it kind of forces us to think about the problem in terms of sequential nature.
Yes, so what you have to decide. Yes.
Danger there, huh?
So we need a new way of thinking about software which doesn't worry quite so much about efficiency and produces code produces code that more naturally expresses the original application. That is the only chance. And I think many people would agree on that. The problem is all attempts to do this, possibly due to lack of money, that they just haven't put enough people on it, but all attempts have failed. I don't know of any, well, except in the database area.
In the databases, because there we, from the application developer's point of view, we raised the level of abstraction enormously. And we struggled very hard to make that efficient, to evaluate those expressions efficiently. We managed to do it. We managed to do it, but it's taken 25 years.
I would throw out graphics as another example where they've been very successful at exploiting parallelism. And so if you look at graphics processing units, they're highly parallel. Basically, they can take all the existing stuff you're building in the 90s and put them on one VLSI chip. And so they've been very
but those are
They've
using...
been so successful that some people in scientific computing are trying to figure out how to use a graphics engine for something that wasn't tool work.
But I think the feature that both of these problem areas have in common is that they wrapped some specialized domain and basically said, look, we're not going to try to do general purpose computing. We have, some very specific set of problems. They're not Turing complete. We don't expect our compilers to discover algorithms. I mean, can you imagine writing a compiler that can discover algorithms for matrix inversion and things like that? So I think you take these problem areas that are small and self-contained, you wrap them, and you say, okay, now I have this thing that can solve that problem. Maybe that suggests a possible problem, a possible solution here. Maybe a possible solution is you take particular classes of problems that you know how to parallelize. You make sure you can parallelize those, and now you tell the application programmer, go ahead and use as many of those as you can, in your programming abstractions. And I understand we're not going to discover parallel matrix inversion, algorithms, but use these tools as best you can.
The area where this stuff founders is when you basically collide with the memory system and the caches. That's for these multicores. That's where it founders, is when you collide with the memory system. Or you can say when you collide, as you say here, the layout of the architecture and the description of the problems don't fit together very well. And that's where we run into all kinds of problems. And so that's the problem is, yes, we can do this for simple areas, but can we do it for other, how much can we extend this is the problem.
How general
and the problem is really, it comes down to the memory system or the layout, a topology of your computer, and matching your problem to that. And that's where you founder on communication and things like that. And that's why MPI, I think, has been so successful, because it forces people to deal with the central problem.
That's right. MPI allows the user it's what the computer is doing, so it allows the user to express what the computer is doing. So it actually has two advantages. One, you can map it onto the computer. Also, you know what's going to happen. Because one of the weaknesses of the other approaches is they got completely unpredictable results, because you had no idea what the compiler was going to do. With MPI, you know what's happening. You can tune it straightforwardly. You know what the problem is doing, because you wrote the problem that mapped onto the computer. As I've mentioned earlier, the library approach, which if you like generalizes the database and the graphics examples, the library approach is the one used in scientific computing. People build, PETSI is a well-known scientific library. People build libraries, and those libraries are used. You do not build conjugate gradient solvers ab initio each time. You just use a library. And that's where all the parallelism usually sticks in libraries. All right, so we can use high-level concepts. OpenMP is an example of annotating, which is trying to put back the information you threw away. And then you can even try to use runtime information, but that's harder. So this is why software cannot be parallelized. This is actually a pretty good piece of software. Dell does not like me that I'm not using a Dell charger. I have not found out how to switch off that notice. I try to remove as many applications as possible, so it would not. Anyway. All right, so this came from another article discussing the network structure of a piece of software. And so this is GridSphere, which Savas would know. It's a nice portal software written by a very good programmer, Jason Novotny. And the chance of parallelizing that is essentially zero, because it's got a lot of connections.
But
Which
they need parallelizing.
What?
Is there a need for parallelizing?
Not especially. I only chose this because I found that. Although I keep trying to get these people, I mean, as a side point, to use services inside portals, because they actually bundle a lot of stuff inside a portal. So this just points out that the traditional way of expressing software produces lots of dependencies which are either gratuitous or extraneous, depending on what adjective you would like to use. Bother. Here's another example. I had a poor student. I asked to work on the Batic Scalable Vector Graphics browser, which is Apache software. And this has suddenly got a model view control structure. The way the software was written is not possible to break it up. There's some long Java sausage running through the entire application, which stops you from breaking it up into M, V, and C. That's just three-way breakup. So the traditional ways of building, these are just two examples of which I found of software which show how expressing the problem in software does violence to the structure of the application. And that is why it is very hard, fundamentally why it's essentially impossible to parallelize automatically. And I think one should assume it's impossible to parallelize automatically anything except something which has been written very carefully.
But allow for some delays, you know, is that going to make that work?
Sorry?
Allow for some, well, I know there's some sequential, you know, some of the sequential nature of this problem, for instance, that comes from the pattern we talked about earlier on. If you allow for certain delays, you can break up.
Not if you have dependence. The trouble is, you see, you don't know what the dependencies are. You have no idea whether, in general, whether this dependency stops you from parallelizing it or not. You have you can't find out. There are no rules to allow you to determine whether a dependency is an essential dependency or not. All right. So the end. So this summarizes those statements about general complex systems. I would claim that if you wrote down a general complex system, it's probably not parallelizable. But if you take the complex systems we want to run, at least in science, they are all parallelizable because of the way they were made. They were made in by some sort of repetitive structure, either nature reproducing lots of things or people reproducing lots of things, and it makes it naturally parallelizable. And the only requirement for scientific programs to be scalably parallel is they be big. That is the only requirement. So they must be big. You will not get good parallelism unless the problem is big. Once they are big, the bigness is measured by the grain size, how much stuff is in each CPU, and the formulas for overhead and efficiency tend only, we'll put these down later on, only depend on grain size. They do not depend on anything else, and hardware parameters. So once you have a certain grain size, you can predict the overhead, you can predict the efficiency. It does not depend on the number of processors. That's why Blue Gene continues to scale forever, up to 250,000 nodes, because they just fix the grain size. And the reason why DOE has used these very large machines is they've run bigger problems on each machine. And that's all. I mean, so that's another important point. You will not get anywhere near as good parallel speed up if you run the same problem and you increase the number of cores, because that decreases the grain size as you increase the number of cores. So an important issue to address about the success of parallel computing is what is your grain size? Is it big enough? And as Intel keeps churning out more and more cores, do we have bigger problems for Intel to solve on those cores? Because if the problems stay the same size, then we will find diminishing returns as we add more cores. The scientists have not seen that. They've always run bigger problems. And up to now, they still want to run yet bigger problems. So they're not near the limit of they're not near any limit. And that's so. Yes.
Would you disagree, saying that it's not only about running bigger programs, but we have the potential now to run many different programs at the same time?
Yes, so that's a combination of loosely coupled and tightly coupled. Yes. So you should take the whole meta problem or the meta job mix and say, is the meta job mix? You want to keep the grain size fixed. Whether that grain size is kept fixed by additional functional parallelism / workflow, or just increasing the problem size of the total problem size of the tightly coupled that can be thought of. You can do either, obviously, but in general, you have to keep the total meta problem has to increase in size if you wish to succeed. Oh, well, this is a trivial slide from a long time ago. And this tells you what we do. Every data parallel problem is done in the same way. Chop the problem up into parts and put one part in each processor. So we've done. All right, so here's a commentary about software engineering. So I know nothing about software engineering, except I have never heard any discussion in high-performance computing that's ever mentioned software engineering. And yet, you would have thought they would have similar goals, because both of them are trying to express problems in a way without unnecessary sort of connectivities. And so I find it slightly surprising that good parallel computing wouldn't give you good software engineering and vice versa.
Sort of in scientific computing, you usually have huge amounts of data. And in absolute terms, I mean, relative to Windows, right? Relatively. Whereas I think maybe when you talk about software engineering, you usually talk about programs that are much larger relative to the amount of data they process, perhaps.
That might be true. I just noticed they're both trying to do the same thing. It's a little surprising that the principles of software engineering, which were probably used in GridSphere, would not generate code that was more easily parallelizable. It appears the principles of software engineering allow lots of connections. That's all I know. I don't know much about it. Just a side comment.
Well, I mean, in basic software, you basically have parameters changing all the time at runtime. In scientific computing, you have a fixed size problem. You know what the problem size is, or you know what the cache size is, or you can optimize it for it. So the goal is different over there. Basically, you have a library which basically gets optimized for a button for a certain processor. It's fine, but for a general software engineering perspective, I mean, a general problem, things will vary all the time. So the goals are very different over there, isn't it?
I don't know. I just noticed there's no connection between the fields. I never went to a meeting. I went to lots of parallel computing meetings. I never had any discussion of software engineering during those meetings. That's all I noticed. That's just my comment. This second bullet has an important comment. It is not the number of connections that matters. It is whether the connections are in space or in time. Actually, parallel computing gets easier if there are lots of spatial connections. It gets incredibly efficient. The easiest parallel computing problem is the n-body problem, where you have one particle interacting with all other particles. That is the most efficient, easiest to run, is why the so-called great machine built in Japan won Gordon Bell Prizes, because they chose the world's simplest parallel computing problem with the lowest possible overhead. So lots of connections is not a problem. What is a problem when those connections are in time, not in space. So spatial connections are wonderful. The more spatial connections you have, the more efficient the problem is.
to the neural network of the brain. That's the most natural way.
Well, that's, of course, a much better map to nature than our computers.
That's conventional wisdom. Everybody has a neural network. The major motivation is really the parallelism.
Yes, that's right, yes. Okay. I mean, neural nets look a little more like nature, because neural networks are a set of entities with state and with connections. Well, that's what Mother Nature is. This grass has state, how big it is and what color it is. And it sort of is connected to roots and to other pieces of grass, and it grows all on its own in locality. So that's why I said the architecture, the neural network architecture is much nearer nature than a parallel computer is, because you have CPUs and memory, and that's not the architecture of most applications. All right, this goes through another simple example. I'll go through this quickly. So here's a 16 by 16 grid. You have your standard sequential algorithm, which this is Jacobi's algorithm. You just replace the value at any one point by the average of its neighbors. So the complex system which this corresponds to is just a two-dimensional mesh. And so you just apply that update some continuous on every point, and then you iterate continuously in iteration time. Then you parallelize by decomposing it. So here's 16 nodes, each with 4 by 4 in each mesh. And this is trivially parallelizable. And the only cost is the communication. That you must now communicate. Those edge points need to be communicated to be able to do the update of those green points. So this is the structure. This is a trivial example, but this has the essential structure of every scientific application. You take your data domain, you divide the data domain up into parts. In MPI, you write the code that programs each part. In this case here, you write the program that codes one of these parts. And you have some if statements to find out which part it's doing. Then you identify what you need to communicate to be able to do a successful update. You do that communication, then you update. Then you do the communication again, and then you update. So these problems always have the so-called, they always have this phased effect. You communicate, calculate, communicate, calculate, communicate, calculate. That's the classic structure of these problems. And if you want to make the communication go down, you just increase the size. So these green points are the grain size. Here we have a grain size of 64. Previously had a grain size of 16. If you count the number of edge points, the edge points here is 32. Previously the edge point was 16. So by multiplying the number of points by 4, we've reduced the communication by 2. And so that just says that the communication cost goes like 1 over the square root of the grain size. And so that's just communication as an edge effect.
Let me add a comment here, this problem I call the being hostage to the slowest guy. I mean, this way of mapping it onto nodes and so on works fine if the work that each node has to do is fairly predictable.
Yes.
But if it's quite unpredictable, then the whole system is going to depend on the slowest guy in each phase.
That is correct, yes.
Right? But that's not a concern in scientific computing. It hasn't shown up as a big issue.
Well, yeah, we can discuss that. So let me see if I have another example. I have a good example of this later on. It's not, I thought it was nearer here, sorry. I shouldn't have gone too far. So, in scientific computing, that problem happens. And the simplest, one good example of where that happens is cosmology. When you're evolving galaxies or stars or whatever in time, and as they get near each other, they tend to cluster, and the amount of work per point, per particle, gets much higher. However, it gets higher it's dynamic, but once it's got higher, it stays higher for some period of time. So you can solve that problem by dynamic load balancing. You do the decomposition, but you move your particles from processor to processor to balance the load. And as the load, because these scientific problems are determined by differential equations, if these differential equations are stable, you can't have huge changes on any one time step. So from time step to time step, the change in load is small. So once you've load balanced, say, to 10%, that 10% will stay okay for some period of time, then you can change it again. Actually, in some of the cosmology codes, they do the load balancing every time step because the load balancing is a negligible cost. So, I mean, the other way you can try to address this problem, so there are two sort of approaches to load balancing, which again I illustrate in several slides ahead. One is, the stupid Dell thing.
Don't worry.
So once it's done that, it won't. All right, so this is domain decompositions, where you actually you try to form geometric units which you put in each processor, and that is appropriate for these relatively slow, from time step to time step, slowly varying cases. If another approach is the so-called scattered decomposition, where you take a domain and you just assign processors, if you like, at random to points in the domain. The scattered decomposition is much less sensitive to time variation and is therefore more appropriate for rapidly varying cases of the type you mentioned. The problem with the scattered decomposition is that you have much higher communication cost, because here we're gaining enormous. These will give you for the slowly time varying cases, these give you the best decompositions, because that's a mathematical fact, that these are the optimal decompositions. These types of decompositions are always optimal. You minimize edge over area, which means you want square blocks. You don't want, like if you have a three-dimensional problem, you do not divide it in 2 dimensions. You divide it in 3 dimensions, because that gives you edge over area over volume has to be minimized. So you always try to try to get as near a sphere as possible as your basic domain. But I'm not aware. I mean, again, these things are tiresome, but they work, and people have not found trouble in doing this. But it's an example of something compilers would find very hard to do. Some of these difficult problems, whereas people can usually think it through because they know a lot about the application, what's varying, and things like that. So when you have a person looking at a problem, they can do a lot more than they can put in some intuition that they know what the result looks like, so what will work.
But this is exactly the kind of information you actually need to express so that the machine, the compiler, could take advantage of it.
Great. So we're now defining the Microsoft initiative in high-level parallel programming. This has so far failed. My impression is it could well have failed because not enough effort was put into it. Because it is certainly true, it's relatively obvious by all of these problems. Well, there's no miracle here. I don't think there are any, and that's another statement I want to make. There are no miracles. I know of no problem which scaled, which got lots of parallelism, which it wasn't obvious that it should have got lots of parallelism. And you can look at it and analyze it, and it's quite obvious why the parallelism was there, and what the issues were, whether it be communication or cache or whatever. It's relatively obvious. You can just look at the problem and see. Because these problems all have natural structure, and we understand very well what causes these difficulties. It's not like GridSphere. I will not tell you how to get parallelism out of GridSphere. That's too hard. But the when I look at the problems, which are clearly stated as linked entities evolving in some iteration space, there you can analyze it and discuss it, and you can, I think, understand the parallelism straightforwardly, and you can estimate how much parallelism you will get. As far as I don't know of anybody who has unexplained successes or failures. All right, so this is an important, I have more detailed slides on this, but this is an important general comment on what happens on that class example. So we can predict very precisely and understand efficiency and speed up. So if you have an execution time on P processors, and you have some efficiency, which is by definition the observed speed up divided by the number of processors, the correct thing to look at is the overhead, which is I define here, which is the P times the parallel processing time minus the sequential divided by the sequential. And the reason why you want to look at overhead is it's linear in this parallel time. So if you have any overhead, it occurs linear in the parallel time. The parallel execution will have load balancing overhead, communication overhead, cache overhead. They'll all be linear in that time. So you'll get the prettiest formulae if you look at that overhead. And in particular, if you look at that simple example I just gave for the Jacobi iteration, you'll find the communication overhead is very simple. It's the communication time for a word between processors divided by the calculation time for a floating point calculation on that CPU divided by the square root of the grain size. And all scientific problems have overheads like that on message when you do explicit message passing. The only thing, they all have this feature that you have a ratio of communication, hardware communication performance to hardware CPU performance. That's natural. There is a constant that's 1 for Jacobi, which in general is not 1. It just happens to be 1 for Jacobi. And you always get, at the bottom, the grain size to 1 over the dimension. In Jacobi was 2-dimensional, so it's the square root. Matrices are 2-dimensional, they're square root. If you did 3-dimensional finite elements, you get the cube root. And so so I would claim that for a large class of problems, the overhead takes this form. As far as I know, all measurements have shown this behavior. And it's relatively obvious why it is. And the most important deduction is that you only have to worry about grain size as far as the problem is concerned. That's all that counts, grain size. How big the grain size is not obvious because you don't know what the constant is. And you also don't know what T-com over T-calc is.
The boundary conditions.
What?
When you go to the boundary, then the computation will become a little bit different than what's in the middle, right?
Yeah, but if you look at that, it's actually not as big an effect. I have some slides which analyze that. That's not important. That's a load imbalance effect, and load imbalance is less serious than communication overhead. It's not as big an effect. Yeah.
So also taking on some practical issues like, one particular node may malfunction, right?
Yes.
And that hold down the whole process.
Yes. So if one node goes out to lunch or decides to answer email, this doesn't work at all. Scientific parallel computing has microsecond latency requirements because we're doing communication very often. We're updating a certain number of these little endpoints are being updated, usually often with a linear time in n. Then we're communicating. And the synchronization time is the time it takes to update little endpoints, which is usually measured in multiples of, tens or hundreds of microseconds. If anything happens that delays any one node by that amount, you're doomed. So you need to stop that from happening. And the parallel computing systems are designed to stop that from happening. And so these are, that's what he meant by, that's why I say these are tightly coupled. And so this just gives you a formula for the efficiency, which is just 1 minus the overhead. I forgot the constant in the formula. Well, sorry, the efficiency for Jacobi it is 1 minus t comma over the square root of t float. So this has this very important. This is what's called scaled speed up. The efficiency is constant at constant grain size, and the physicists run at constant grain size roughly. They run bigger problems on bigger machines. It also tells you why they like large memory sizes on some of their machines. They need to get the grain size big enough. For a given communication performance of their machine, they need enough memory to put enough n in there to get a good performance. So machines which have modest memory per node will not run as well as machines which have larger memory per node because they'll have a smaller grain size. So you're able to predict what, and of course that's you can make the constant, as I said, this depends dramatically from application to application. The constant is smallest. I mean, this Laplace is the hardest problem. Usually as the problem gets more complicated, it gets easier. The complication tends to increase, if you make a problem more complicated, it increases the computing more than the communication. That's Fox's theorem or something. It's a relatively obvious statement. If you look at, for instance, CFD, so that CFD has 5 degrees of freedom. Yeah, I'm going to stop around now. CFD has, say, instead of Jacobi with 1 degree of freedom point, has 5 degrees of freedom. So the actual computation of the point goes like 5 squared. The communication goes like 5. And that's a general statement that as you increase the number of degrees of freedom, the computing needed to update those degrees of freedom goes up at a different rate from the communication. QCD, the famous quantum.
5 for CFD?
Oh, it is 5. It's energy, velocity. I have it again in my notes. It's a while since I looked at it, but it is 5. I'm almost certain it's 5.
You're right.
So CFD is, in that sense, CFD is easier than Jacobi's equation because it has an extra factor of 5. One of my colleagues, Norman Christ, built a famous QCD machine to do quantum chromodynamics. Quantum chromodynamics is 3 by 3 complex matrices. That has a very small ratio of communication to calculation because it's complex, which is a factor of 2, gives you a factor of 2 in communication, a factor of 4 in computing, and it's 3 by 3. So all of those make problems easier. So it's worth noting that the difficulty we have with parallel computing is not the complexity of the problem. That's good. The hardest parallel computing problems are the simplest ones because they tend to have very high communication to calculation ratios. The easy ones are the complicated ones. I said the easiest is the n-body problem because each particle interacts with every particle. And so that actually means that when a particle arrives at a node, you can use it to update all the particles on the node. So actually, it's a far, far more efficient algorithm, which is why Great won the Gordon Bell Prize, because they could build very cheap hardware to simulate the n-body problem, because they needed little communication and little memory. Because it's an order n squared algorithm, so it doesn't need much. It doesn't need much memory to use up a lot of computing, and its communication is almost very small.
Are these slides available anywhere?
Yes, they are.
On your website or something? Or?
Yes, there's a URL on the first page.
But also you can give them free and
yes. Maybe we should stop now and I'll go back to the first page.
Could you put up the first slide again so I can copy down the...
So this is recorded, right?
So this is recording, and all the series, all 4 presentations are going to be recorded.
Can you read this thing at the bottom?
Oh, yeah.
Grid start.
Your website.
So yeah, just a reminder that we're going to have 3 more of these until Thursday with, if I remember well, it's only the Wednesday one that's a different time. But you must have all received a meeting request from Microsoft for announcements. Yeah.
If anybody has any requests about things they'd like me to talk about, I'd be happy to talk about them. I prefer discussions to monologues.
This works so fine.
So would you be able to take one of the algorithms like in the Intel slide, maybe drill down to something?
We can try. I try to do that. Yes.
I think that would be nice. We'll probably should find one of those that has a common
Okay.
to most of the people there.
All right.
Excellent. Thank you very much for the day.